In mathematics, often we generate a lot of terms. In algebra, what we find is we have these somewhat complicated terms involving x or y or whatever, and we can use certain types of manipulation techniques and cancellations, factoring, and whatnot, and we can reduce those complicated terms to a fairly simple one. And there is a natural extension of that it uses sometimes algebra, but is more about pattern matching, because mathematics is about pattern matching. And that's this idea of sigma notation. So what ends up happening is, if I have a sequence of terms, so A1, A2, so this is the first term, the second term, the third term, and so on to the nth term, and I want to add them all together. What I might want to do is have a compact notation and a way to write all of them in one single expression. And the way to do that is this idea of sigma notation. So instead of saying A1, A2, A3, all the way to A sub n, I write this sigma, and sigma is kind of similar to the English S, and it's the idea of a sum. So doing that, we have the lower bound and the upper bound. So this is our starting index, and this is our ending index. So we go from the first term to the second to the third, all the way, in this case, the nth term. And n is kind of a placeholder. Usually it's used as, you think of it arbitrarily, and then you solve for particular n's. But anyway, the idea here is you have some sort of index, something that keeps track of where you are, and then you have a starting position and an ending position. Those of you who are familiar with programming, this is what looping notation is, right? If you've ever done a for loop and you've maybe summed, said for I equals 1 to n, and you've, added something to a sum, that construct in computer science directly comes from this. So the idea of summing over a for loop is directly related to this. And why we want to do this is that sometimes this is just a bunch of numbers, and that's not always that helpful, but oftentimes there's some sort of pattern, and we want to figure out if there's a way to express that pattern in a compact way, or maybe manipulate it to arrive at interesting results. And one of the most interesting results that we'll get to in calculus, in fact, involves this. So some simple examples are here. If I start at 1 and end at 5, and the pattern, so this pattern is that at each step, the index is what we're adding. So I add the first index to the second index to the third index to the fourth index to the fifth. Now in this particular case, I believe that adds up to 15. So we could say this equals 15, and that's interesting enough. What we also find is that we could, if we have a different pattern, we take the index plus 1. Then if we started the index at 0 instead of starting it at 1, and we ended it at 4, we arrive at that same sum. So this and this are equivalent representations, even though the pattern is slightly different and the indexing is slightly different. So what this shows you is that most of these sigma sums are not unique. In fact, I don't think there's any way to make one that's strictly unique. And so it might be, for my money, I would probably use this one over this one, because this one just makes a lot more sense to me. I don't have to think about I plus 1. But it's all about what's convenient in the moment. This one's a little more complicated. In this one, the index is going to be squared. So 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Again, we started at 3, so we do 3 squared, and we end at 7. So we continue this pattern all the way up to 7, and then we add all of them together. And so we're just kind of walking through. Now this one, the pattern is probably even more exotic. We take 1 divided by the index, the square root of the index. So we start at 1, so we do 1 over the square root of 1, and then we go to 2, 1 over square root of 2, to 3, 1 over square root of 3, all the way up to 4, and that's where we stop. And you might be thinking to yourself, well, why are we doing this stuff based on the index? Well, what we generally find is that we find a pattern and we find we're summing it up, and we kind of go backwards. We start with the pattern and then we figure out what the indices are. And that's kind of it's kind of odd. You're not usually saying, oh, well, I've got some indices and I've got something I'm doing based on the index. You usually start with the pattern and work your way back. This is an ever more complicated one. Now in this one, I start at 1, but I don't actually end at an explicit number. I end at some number n. And then I have n also in the expression here, but I have the index. So how do I approach this? Well, what we need to remember is that even though this is an n, and you might think of that as some sort of variable or parameter, when we think about sigma notation, the only thing you change is something related to the index. If it's not related to the index, do not change it. So in each expression, this 1 over n stays. It doesn't change because we're not indexed on n, we're indexed on k. So k is 1, k is 2, k is all the way out to n. Now we have to use this sort of ellipsis notation because we don't know how many terms. If it was 5 terms, we could write it explicitly. But in this case, we don't. All the more reason not to write it this way, because I mean, most mathematicians and people familiar enough know that these are equivalent, but there's a little bit of haziness, a little bit of hand waving here. So we prefer to use expressions like this. But again, we started at 1, 2, and then we finished at the stopping point, at that upper bound. And then we changed the value on that index. So if I didn't use this ellipsis here, that would be 1 over n 3 squared plus 1, 1 over n 4 squared plus 1, all the way to whatever n is. N might be 100, it might be 100 million, it might actually be 2. If it was 2, we wouldn't even need this piece. We don't know, but so we just represent the generic pattern here. Moving on, we arrive at something even less explicit. We now have some sort of delta x and f of xi. So in this particular case, what we're doing is we're saying, okay, there's some sort of x that's being indexed. And I don't know what that x is. But if I just want to follow the pattern, let's say I have no idea what I'm doing, but I know what the pattern is. All the pattern tells me is I take this thing and I replicate it. And the only thing I change is something that matches the index. Well, if I do that, okay, well, in the first term, the only thing with an I is here. So it's got to be f of x1 delta x, okay? And then the next term, the only thing with the I is here. So it's f of x2 delta x, f of x3 delta x, f of x4 delta x. And then I end at n, so it's f of x n delta x. And that's where I get to. And I know that seems very complicated and kind of, it's probably very hazy to you, but the idea is we want to get comfortable because particularly this piece is going to be very, very useful to us in terms of definitions. Because what this is representing is, this is sort of that delta x is that width. Remember, we think of delta x, we think of some sort of change, some sort of width. And this is the function value at some point. At some point. And we don't know what points are. We don't know what points we're picking. We don't know what x1 and x2 and xn are. We have no idea. But we're going to use this construct to come up with some very interesting things as time goes on.